I'm adding this podcast after talking a little bit about CMIP 6 projections of extremes. I will add more podcasts of CMIP 6 projections once the final version of CMIP 6 is released, which I may already have said somewhere else. But the difficulty of relying on projections is to understand what's happening in the past and whether the models have captured this. We already mentioned that the models have had difficulty in producing the historical trend in monsoon seasonal rainfall, which has been decreasing, and that's most likely because they don't have the impact of aerosol properly represented in terms of the solar dimming and less warming of the land despite its low heat capacity compared to the ocean, which is our major hypothesis for why monsoon has decreased. And all the models also project that monsoon will recover in the future, which could be because again the aerosol impact is not properly represented. So it's good to visit this little podcast here because it has some connections between different aspects of the monsoon changes that are observed in the historical period, and the models obviously are not capturing these in great with great accuracy. Okay, so these are papers from Arindam Chakravarti's group from IISc, and he writes really nice papers, very quiet guy, unlike many who make a lot of noise. So I will connect a few dots with his two papers here. So his work I already mentioned. This is looking at time series of the cumulative variance explained by the significant eigenmodes in percentage of the interseasonal band 8 to 90 days that represents oscillatory behavior with periodicities of 20 to 60 days, 10 to 20 days, and sees the time series of the calculated percentage of the total daily variance explained by 3 to 9 day filtered rainfall averaged over India every year. Okay, the trends are significant by statistical tests. What is the main message? The main message in this paper is that the intensity of the low frequency intraseasonal oscillations, so 10 to 20 days, is not changed much, whereas the 20 to 60 days has significantly decreased in intensity, which can be seen as the rainfall variance over these time scales, and that is related to the number of extremes occurring in these periods. So you have to explain the consistency between the distribution of extremes in the season, changes in the active break periods, and changes in the seasonal mean, right? So this drop in the intensity at 20 to 60 days mainly is compensated by an increase in the intensity of daily variance of rainfall in the synoptic scale, which is 3 to 9 days. Okay, so that's one signature. So this is not just saying extremes are increasing and they're becoming widespread and so on, but this is looking at the time scales at which these sporadic extremes are happening. The other paper looks in more detail at what the mechanisms are and how they are consistent with each other. So here we are looking at the total number of extremes over this period of 1950 to 2010 or so, 1951 to 2013, between May and October. So the number has clearly increased, and he's showing also the number of extremes happening in the break phase, which has increased. Number of which have increased, number of extremes happening in the transition phase from break to active, which is also increased, whereas if you look at the number of extremes during the active periods, they have actually decreased. And here we are looking at the number for the pre-1980 period of the a number of extremes. So let me make sure I got this right. So spatial distribution of the percentage of extreme events that occurred between May and October during 1951 to 1980 in the negative break, so in the break phase, in the transition phase, and in the active phase. Okay, this is before 1980, and here we are looking at the difference of the extremes that happened during the break phase between post 1980 period and the pre 1980 period. It's positive for the break period and the transition period, but it's mostly negative for the active period, except for a few spots on the Western Ghats and the Himalayan foothills, and there is a little spot here. So the core monsoon zone during the active phase has seen reduced number of extreme events. Okay, so this can explain the transition changes in active to break, as well as the reduction in the mean monsoon while also increasing the extremes. Okay, so we have to explain all these features together. So this paper looked at changes in extreme events and daily climatology during June, July, August, September, the monsoon season. So it's looking at relative change in extreme events from a model that they use to understand the mechanisms and observations, and basically you are looking at the relative change in extreme events during June to September, during the active phase and during the break phase. So in the model, the change during the break phase is a little bit exaggerated. In the observations, the change in the active during June to September, the season versus the active phase and the break phase is basically consistent with the model, or the model is consistent with the observations. So the change from pre to post periods, pre-1980 to post-1980, is also shown in the model and observations. As we saw, the post-1980 has reduced number of extremes during the active phase compared to the pre-1980 phase, and this is the change in the strength of low frequency intraseasonal oscillation mode. Explained variance of low frequency ISO over central India from the model. So it's showing the warm and pre and post 90 simulations and observations pre and post 90. Both model and observations, both for model and observations, changes in mean are significant at 5% level. Change in spatial distribution and the percentage of the variance explained to the total rainfall by the low frequency ISO from the model and observations during JJS months. So the significance is shown here. So again, the point is to show that the low frequency ISO variance over central India has decreased both in observations, and the model is essentially able to capture this response, which is presumably related to the warming that has happened in the post-1980 period. There is also a so-called climate regime shift in the mid-1970s, but we will not go there right now. We will just focus on the warming. So how does this change in the distribution of extremes during the break periods versus the active periods affecting the transition from the break to active periods and the intensity of the break and active periods? Remember, in the Singh et al. Paper, the review paper with Roxy and Subimal and so on, and her 2014 paper looking at the changes in intensity of the active and break periods, she had shown that the intensity of the active period had increased, whereas the break periods had become less intense, more in frequency, and even the active periods at shorter time scales were argued to be increased by another paper by Pai et al. And so on. So here are the processes that the model is able to extract by reproducing the observed behavior. Let's say you have more extreme rainfall events in breaks. That increases the atmospheric stability, which produces less rain in active phase, and it decreases the seasonal mean. So there is a consistency check there. The less rainfall in active phase also produces decreased variability in the low frequency ISO scale, which is consistent with the first paper, and that leads to reduction in low frequency ISO intensity, which is also observed. Okay, and the other feedback you have here is that more extreme rainfall events in break are related to are going to produce a weaker easterly shear in the transition phase, so going from break to active, and that is also again going to result in less rain in the active phase and also favor more extreme rainfall events in the break periods. Okay, so there are multiple timescale interactions here. There is a dynamic and thermodynamic response in the monsoon system like anywhere else. So you are always looking to see, with the ocean warming, land warming, and the contrast changing, how is the circulation changing? How is the moisture supply changing, and how is the actual monsoon response changing? And that response is obviously split into seasonal downward trend and increased extremes, but the distribution of the extremes in active and break phases is critical, because that is also changing the frequency, duration, and intensity of the active and break periods by altering the transition between the break and active periods. Okay, so just to repeat it, the flowchart for the mechanism of the decrease in seasonal mean and low frequency intraseasonal variability strength over India. Increased extreme rainfall events in break phases weakens the easterly vertical shear over the northern Indian Ocean region. If you don't understand the relation, you can look up the intraseasonal oscillation short course I have on my channel as well. And basically that vertical shear is critical for northward propagation and mesols and the intensity of the low frequency intraseasonal variability. So if you weaken the vertical shear, you're going to weaken this low frequency intraseasonal oscillation timescale variance, which is consistent. Okay. This weakens the instability, causing lesser convective activity in subsequent active phase. Stability over central India has increased when we have more extreme events, especially during the breaks. So extreme events are going to keep releasing the instability in the system and make the system more stable. Stability over the CI has increased when we have more extreme events, especially during break periods, because break period is already more stable compared to the active period. Weaker vertical shear creates favorable conditions for the growth of deep convective storms. Since majority of the reduced stability and weaker vertical shear, since majority of the seasonal mean rainfall occurs during active phases, this decrease in active phase rainfall decreases the seasonal mean. Okay, so if you increase stability, then you're going to increase the vertical shear, so then conditions for growth of deep convection is reduced or made unfavorable. Reduction in active phase rainfall also incapacitates variability in low frequency intraseasonal timescale, which in turn weakens the low frequency intraseasonal oscillation intensity. Okay, so this series, these two papers, there are others from his group as well, I like very much because it systematically connects the changes in the low frequency and synoptic timescale intraseasonal oscillation intensities. And when we say intraseasonal, usually we mean 10 to 100 days, 9 to 100 days used here and so on, but synoptic time scale is increasing the intensity of extremes, compensating for intensity of rainfall variance compensating for the decrease in low frequency intraseasonal variability. So it's good to have these consistency checks, which are not always done, and models, especially in terms of projections, have to be watched carefully, because in the historic period they have not only not been able to reproduce the observed downward trend because of aerosol problems, but they have deficiencies in simulating the active break periods themselves, which means the changes in extremes and the distribution of the extremes in the active and break periods is also very challenging for the models. So just be careful of that when you look at projections of monsoons and monsoon extremes in the models, also keeping in mind that the shorter term projections are severely affected by or largely affected by model uncertainties, but the longer term projections are affected by scenario uncertainties. So all these things have to be kept in mind.